Welcome back, everyone, to another explainer. Today, we're tackling one of the most frustrating, but honestly fascinating, challenges in our field, near-surface seismic imaging. If you've ever spent weeks trying to clean up land seismic data, only to be left with a messy, uninterpretable stack, you know exactly what we're dealing with. Today, we're going to break down the heavy mathematical concepts and the massive paradigm shift happening right now in how we handle near-surface anomalies. We'll look at the theoretical models, and we'll explore exactly how these advanced datuming schemes actually work in practice. Here is our roadmap for today. We'll be covering the near-surface challenge, advanced workflows, model-based dynamic corrections, data-driven interferometry, a really cool Chinese foothill case history, and we'll wrap up with some key terminology.
Section 1, the near-surface challenge, and exactly when statics fail.
Okay, let's dive right into this. The absolute nemesis of land seismic data? Near-surface velocity anomalies. We all know the baseline assumptions behind surface-consistent statics corrections, right? We assume a vertical travel time correction that might work for deep reflections, and we assume that at any particular surface position, there's just one single static shift for reflected waves, completely regardless of their incident angle or azimuth. But as our source material so pragmatically and kind of humorously points out about these assumptions, when does that fail? Who knows? Just try, and then you will learn from the brute stack. It's literally a trial-by-fire approach, and frankly, in highly complex geology, it totally falls apart. So why does it fall apart? Well, when you're dealing with rugged topography, massive weathering layers, overthrusts, or sinkholes, that straight-ray assumption of conventional statics is just completely destroyed. I mean, we're talking about near-surface environments where the P-wave velocity can violently swing from 340 meters per second in loose dirt to 6,500 meters per second in hard bedrock over incredibly short distances. Under those extremes, basic ray tracing and conventional statics simply cannot resolve the kinematics. The energy scatters, the wavefronts distort, and your image is totally lost. Section 2. Let's look at advanced seismic imaging workflows. If statics fail, what's our next move? Let's ground this complex math by seeing exactly where these advanced solutions fit into a modern researcher's workflow. Take a look at a standard pre-stock time and depth imaging workflow and notice steps 2, 4, and 6. Deriving near-surface static solutions, picking RMS velocity fields, and deriving that interval velocity model, those aren't just push-button automated processes. That is high-end research. That's where the heavy lifting actually happens. To get to a clean pre-stack depth migration, or PSDM, at the very end, we have to meticulously manage the near surface early on, which often means integrating wave field datuming right during our time migration phase. Section 3. Model-based dynamic corrections. This is where we abandon those straight-ray assumptions entirely and use wave theories to physically propagate the data through a near-surface velocity model. Within these dynamic corrections, there are two primary methods, and it is absolutely crucial to understand the geometry requirements that tell them apart. Wave equation datuming is super strict. It requires perfectly even, regular spacing for both your shots and your receivers. If your data isn't perfectly regular, you gotta regularize it first. Wave field datuming, on the other hand, is a bit more forgiving. It only requires regular receiver geometry, so it completely avoids the headache of dealing with common receiver gathers. Let's focus on the explicit process for applying wave equation datuming to common shot gathers. It's essentially a two-step mathematical journey. Step 1, we take our data and do a downward propagation using a true near-surface velocity model. We use a one-way wave equation extrapolator, think of a phase shift method, to push that wave field down to an intermediate datum. Step 2, we do an upward propagation from that intermediate datum up to our final floating datum. But here's the trick. This time, we use a constant replacement velocity. This brilliantly strips away the chaotic near-surface effects and gives us a much smoother interface that's infinitely better for our subsequent migration. Now, what's really interesting about this slide is how it visually anchors that abstract math. Check out these wavefronts. You can clearly see the downward continuation of both the forward and reverse travel times straight through the model. We're not just shifting traces up and down by a few milliseconds like we do in conventional statics. No, we are literally mathematically repropagating the entire wavefront through the complex velocity structure, and we're accounting for every single diffraction and velocity pull-up along the way. Moving to Section 4, Data-Driven Interferometric Redatuming. So the crucial point here is this. Model-based dynamic corrections are fantastic. But what if your near-surface model is just wrong? Getting a highly accurate velocity model for the top 500 meters is notoriously incredibly difficult. And this brings us to a massive paradigm shift: data-driven methods. You see, model-based approaches live or die based on the accuracy of your near-surface model. If the model's flawed, your downward continuation is flawed. But data-driven methods, like interferometry and the common focus point or CFP method, they skip the near-surface model entirely. By cross-correlating seismic traces, the phase of the common ray paths traveling through that messy near surface naturally cancels itself out. The computational and workflow benefits here are just huge. You save an incredible amount of time, and you avoid cumulative errors, simply because you don't even have to build that complex shell of velocity model in the first place.
But of course, this introduces a pretty obvious logical hurdle. If you throw away the near-surface velocity model, you're probably asking yourself, wait a minute, how do I know where the reflection is actually coming from? Without a model, how on earth do we correctly place the reflector in depth?
To solve this, we rely on the mechanics of interferometry. Here are the key iterative steps. First, we associate fake VSP geophones in the subsurface with fake direct arrival traces. Then, we perform correlation loops between different shot records. Because the waves travel through the exact same near-surface path to get back to the surface, correlating them actually subtracts that shared travel time. This effectively turns a surface receiver into a virtual subsurface source. Finally, we iterate. We use reflection picking to continuously refine the position of this virtual reflector. But a quick word of warning here. Because we don't have a velocity model to fall back on, your reflection picking strictly and heavily impacts the final image quality. It really requires an expert eye.
Section 5. Let's look at a Chinese foothill case history. And this brilliantly illustrates the real-world stakes, proving that these aren't just academic math exercises. These grid models are from a case history in the Chinese foothill overthrust. Just look at the incredibly rugged topography on the surface, and right beneath it, those massive rapid velocity variations. You can see those bright pinks and reds sharply contrasting with the blues and greens. Conventional statics would completely choke on this data. There's no way. It was only by applying these advanced wave equation datuming schemes that researchers could strip away the near-surface chaos and finally reveal the deeper thrust belt structures that are absolutely critical for exploration. Section 6. Key Geophysics Terminology. Let's kick off a rapid-fire review of the key terms to really solidify these concepts for your academic toolkit. First up, statics. This is simply applying vertical time shifts to each shot and receiver position. It's our baseline correction method that desperately tries and honestly in complex geology frequently fails to fix land seismic data by making the big assumption that wave paths just travel straight up and down.
Next is wave equation datuming. This is our dynamic, model-based method. It uses a one-way extrapolator to downward continue data through a known velocity model, and then upward continue it using a replacement velocity. And remember the golden rule here. It strictly requires even, regular geometry spacing for both your shots and receivers. Then we have interferometry. This is our data-driven hero. It redatums seismic data by correlating traces. Through the phase cancellation of common ray paths in those correlation loops, it allows us to completely bypass the need for a near-surface model. And closely related to that is CFP, or the common focus point method. This is the ultimate data-driven tool that actually redefines migration. It breaks it down into a focusing step in emission and a focusing step in detection, which again allows us to skip that messy near surface entirely. Let's move to our final slide and see how this all builds into a massive question for the future of our field. If interferometry and data-driven methods allow us to skip the near surface completely, saving immense computational time and bypassing model errors, will near-surface velocity model building eventually become a total relic of conventional processing? It's a really provocative thought and one that is actively driving the bleeding edge of geophysics research right now. Thanks so much for joining me on this deep dive. Keep questioning those standard workflows, and I'll see